Welcome in our lecture Fundamental of Casting and Solidification. We are going for lecture 13. Now we will start our solidification courses section where we will discuss about solidification time calculation. So mostly we will go for heat transfer calculation in around 10-20 lectures in that. So how to calculate solidification time, how to track interface and what position interface will be there, and what will the temperature of the interface. In pure material, it obviously it's melting point, but in binary system it's continuously changing, so you have to track that. So all thing we are going to discuss in this. Similarly, we are going to also discuss about directional solidification where growth is uniform velocity. Okay, your interface is moving at a constant velocity. Similarly, we are going to also go into materials part. Okay, in that we will understand the dendritic growth, equiaxial growth, planar interface, how these are growth is happening. Similarly, we will understand the composition track of the liquid. How can we track the composition in liquid in binary system? Pure material, obviously there is no impurity we assume, so there will no composition change, but in binary or multi-component systems there will composition is continuously changing, so you have to track that. So we are going to discuss in detail these things. So before a start of these sections, we will go basic heat transfer first. Okay, basic concept of heat transfer in castings. Okay, then we will derive our basic governing equation. Even you have not done heat transfer courses, you can go through this course and you can understand. Okay, first we will start with basic heat transfer in casting. Okay, so there are three mode of heat transfer. First is conduction. Obviously we know that conduction. Second is convection. Third is radiations. Three mode of heat transfers. Okay, conduction, mainly we are going to focus about conduction and some amount of convection. Okay, so conduction is our main topic for our casting purpose because there is a solid body. Okay, so what is conduction? If okay, if let us assume you have kept one body, there is one body, solid body is there. Okay, and you have kept TH and here is TL, low temperature. Without temperature difference, like what is happening, why fluid is flowing, why fluid flow? So due to pressure gradient, isn't it? Similarly for temperature, without any temperature difference, not temperature, there should be temperature difference, only heat will transfer. Okay, heat transfer happens due to temperature difference. Okay, if there is no temperature difference, there is no heat transfer. Any mode of heat transfer will not occur if your temperature difference is not there. Without temperature difference, there is no heat transfer. Okay, very clear. So there is a temperature difference, that is TH and TL. Temperature H is indicating high temperature, TL is low temperature. Whatever value you can keep, even 1 degree, the heat transfer will occur. If TH equal to TL, then heat transfer will not occur. Okay, if temperature difference is there, there is always heat transfer. Okay, and what happens here, the molecule at this layer is going excited in state due to its high kinetic energy, and it start to collision and vibration molecular level. It transfer its kinetic energy to next element. Similarly, it go on and transfer our energy from high temperature to low temperature. This mode of heat transfer is called heat conduction. Okay, so we can say in metal, free electrons, okay, due to movement of free electrons. So what happens at high temperature, excited state TH, in metallic systems, electrons start to go excited and start to transfer the energy from toward the lower temperature regime. Okay, so heat is transferred from high temperature to low temperature. Similarly, for solid non-metals, collisions, molecular lattice vibrations happens. These vibrations also can transfer the energy. So what is happening? It in this case, molecular level amount of energy transfer from high energy to low energy regime. Okay, if temperature difference is not there, so there is no change in kinetic energy, so no transfer of energy. Okay, due to that we can understand At the molecular level, transfer of heat occurs due to free electron in metal. In non-metals, collision of molecules, lattice vibrations play roles in solids and gases. Okay, it happens in all the medium, solid, liquid, gas stage. Okay, so and this is known as conduction. Okay, where is convection? Convection need one important thing, temperature difference, obviously del T. Okay, obviously without temperature difference there is no conduction or convection or radiation. Okay, so if there is temperature difference and there is a bulk movement of fluid, bulk if there is a bulk movement, okay, then we can say there is a convection. What is conduction? There is also del T is there, but what is happening at molecular regime, molecular point, molecular space, point, what is happening? Energy is transferred. So there in velocity will be negligible. Okay, velocity is negligible, but in convection a reasonable value of magnitude will be there, okay, like micron per second in droplet. Okay, you will not see nano scale, you will see micron scale at least, micron scale in droplets, small scales, scale, cm scale, meter per second scale, kilometer per hour, something like kilometer per second kind of scale you can see in convection. Okay, depend on the situations. Okay, so what is needed in here? Bulk movement, fluid should move. Okay, then only convection will occur. Conduction doesn't need any motion. Okay, but motion happen at the molecular level. Molecular level there is a motion of electrons, ions, okay, and molecules, lattice vibrations. These things happen in conduction, but where is convection? It needs a bulk movement. Okay, so and radiation does not need any movement. Without that also heat can be transferred in vacuum also if temperature difference is there. Okay, so we are not going to detail in the radiation and convection also, we are going into conduction. Okay, conduction suggests there is a x length th TL. Okay, if any temperature difference is there, conduction proportional to del T absolute, that is equal to Th minus TL, Th minus TL, del T is equal to Th minus TL, also inversely proportional to distance. Okay, 1 by x, thickness. If more thicker, heat transfer will be slower, isn't it? Okay. Similarly, proportional to area, surface area, cross section, let us assume 3 dimension. So, this area where heat transfer is happening. Okay. So, we can write del T x into A. Okay. If we remove, so we say rate of heat transfer, that is equal to Q, and unit is watt, that is equal to minus K del T by del x into A. A is the cross section area where on the perpendicular heat transfer is happening. K is thermal conductivity. Okay, and del T by del x is thermal gradient. Okay, thermal gradient. Some if you are taking one dimension only, so you can write Q equal to minus K dt by dx into A. In one dimension, temperature is depending only function of temp x. Okay, that is depending only one direction. Okay, So, this law is called Q equal to minus K A del T by del x is known as Fourier's law of heat conduction. Fourier's law of heat conduction. This is known as a Fourier law of heat conduction. Okay. So, now we will go for it is in one x direction. Someone want Qx minus K A del T by del x. Similarly, heat flux equal to Q bar double dash Q double dash. What does it mean? Divided by area. So, minus K del T by del x equal to Q by, isn't it, in x direction. Similarly, Q y minus K A del T by del y, heat flux in y direction minus K del T by del y equal to Q y by A. Q z equal to minus K A del T by del z, heat flux Q z double dash minus K del T by del z Q z by A. Okay, these are the heat flux. Okay, heat flux is a vector quantity. Okay, you can understand from this equations. Okay. So, if want to understand, we will go for energy equation for the 3-dimensional system. So, we will take a semi infinite, we will take a body, okay. We are taking a, we select an meant of volume, control volume, volume, okay, for energy conversion, which has, it has volume of dx dot dy dot dz, okay, and apply principle of conservation of energy, the first law of thermodynamics. Okay. What's the first law of thermodynamics? That suggests rate of heat added plus rate of heat generated if minus rate of heat removed equal to rate of energy change within element. Okay. So, we are selecting a control volume, this L, B, H is there, and in that we are taking a infinitesimal control volume which has dx, dy, dz. Okay, we are taking a small control volume, and we are ignoring the third dimension to visualize easy way. Okay, so just we are taking okay, even we can take that. Okay. Okay. So, you will understand 2D, we will just write in 3D. Okay. It is easy to understand in 2D. Okay. So, we are taking 2 dimensional. So, what is energy conservation is saying E dot in plus rate of heat generated minus rate of heat removed equal to rate of energy change within the element. So, we what is the element? This has thickness of dx. Okay. Coordinate system you can make x, y and z. Okay. This thickness is elemental thickness is dy and this depth is dz, isn't it? So, E dot in, and what is first law of thermodynamics saying, rate of heat added E dot in dot is saying rate, okay, plus E dot G minus E out equal to energy change within the rate of energy change within the element, okay, that is E dot. So, we can write down, we have to write our what is happening. There are two kind of mode of heat transfer can happen. We are just writing about conduction only. So, what there is a heat conduction is happening, okay, that is written as a in x direction q x bar, that is x heat flux in x direction, and you have to multiply because what you have to calculate rate of heat added, heat we have to discuss about heat, that is in watt. So, not in watt per meter square. So, flux is in watt per meter square, where the heat is watt. So, q double dash is what is that? Watt per meter square. Now, which area you have to multiply? The cross section area, where we are applying dy into dz, dy into dz, isn't it? What is coming out? Q double dash x plus dx into dy dz, isn't it? Similarly, from in y direction, okay, qy dash, okay, and what is the area? Dx and dz. What is coming out here? Qy plus dy double dash into dx into dz. Okay. Similarly, in depth like this we are not writing, but you can understand q z double dash and what is the area? Dx into dy. Okay. I am just ignoring because it will be very not clean in writing. So, I am just removing that. Okay. We can understand what is happening in next direction. Okay. There will be q z plus dy double dash into dx into dy, isn't it? So, q in equal to energy exchanged with the element by conduction first, and what is another way? Let us assume one example. Even you are taking a solid, your hand, there is a flame and you are moving, isn't it? You are moving and coming. If your flame is fixed and you are just moving, let us assume if you are going very slow, okay, very slow, what will happen? Hand can burn, isn't it? Your temperature will change due to mass flow, isn't it? Now, if your velocity is very fast, okay, then what will happen? There will chances that you will not even burn hand, or even you can't feel experience any temperature change if velocity is very high, okay, and temperature is very less, okay, some situations, some cases. So, what is happening? Due to mass motion, okay, energy is exchanged with element by mass motion also, okay. So, we will first write conduction. This is a conduction one, isn't it? This scale is showing conduction one, okay. So, for mass motion, we are writing similar kind of, we are making similar kind of 2D, and we can understand in 3D. So, this is dx okay, this thickness is dy and this thickness is dz, okay. So, this is called energy transfer mass flow, that is rate of energy carried is equal to rho velocity into enthalpy into area, okay. Rate of energy carried by due to mass flow is rho into velocity into enthalpy into cross section area. So, what we can write here in the x direction, what is the velocity? X, y, z direction, what is the velocity? U, v and w, isn't it? So, what will the area here? What is the energy in x direction? Rho u h x, enthalpy in x direction into dy dz. What will come out? Rho u, we are assuming that velocity is constant h x plus dx dy dz, okay. Here what will happen? In out, okay. Here rho v h y dx dz rho v h y plus dy dx and dz. So, we can see the two type of energy transfer can happen. One can be due to conduction. So, we have written that heat flux into area, that is Fourier's law of heat conduction. Second, energy can be exchanged within the element by the flow, okay. If element is moving, let us assume that element is moving. Why we are understanding this thing? It is very useful in casting and welding manufacturing processes. What is happening in casting and weldings, designing these concepts, what is happening? Conduction is very normal in all the cases, but let us assume you are to heat your billet. So, what is happening in reality? Furnace is there, we keep our billet, okay, and it start to move, okay, from one end to another end. At initial stage, what will be the temperature of billet? Room temperature. Initial temperature will be room temperature. As you are moving, what will temperature of billet rises, isn't it? There is a velocity. Let us assume your velocity is very high. What will happen? Temperature will be not too much high in the billet. If your velocity is so slow, there is chance that it can very high heat. So, you have a optimized velocity from you optimize your velocity of the furnace, the blade movement, so that you can get a sufficient temperature like 1200 degrees for forging. So, this kind of concept come in manufacturing. So, I am taking care of energy exchange element in by mass motion. Okay. So, for today we are I am stopping this lecture. In next lecture we will go in detail. Okay. Thank you.